Okay, and we are live.
Oh, really already?
Yeah, we are live. We are live now, I think. Hi,
And
everyone. Can you?
you can see, but okay, I will go on my presentation, but I want to be able to see anything.
Um, yeah, I think the way it will go is that you will finish the presentation and people will ask questions. Meanwhile, then you will answer the questions at the end. So I think it would be fine if you just presenting for now. But at the end, I think you will be able to see the charts and everything again. I think if you don't have a dual screen, is that okay? You
It's okay. It's just the technical issue that I will not be able to see myself. That's what I want to make sure that it is good. So
okay?
I will just be on the slide, completely on the slide. Because she mentioned that, okay, if not my I will not be able to be seen on the screen. So
No,
that
I
means
think
I
can you?
leave it to you.
No, it's fine. It's fine. As far as it's fine from your side, it's fine. Also, if you're fine, you can
Is
start.
it okay? Can you see the difference?
Yeah, we can see the changes. Yeah, and we can
Okay.
see you too.
Okay.
Okay, so welcome to this new KmerAI Talks. My name is Jonas Nyawe, and will be your host today. And we are sorry for the huge delay. It was due to some technical problems, and we hope you will still hear. And thank you for your patience. So let me present our speaker of the day. Adrien Njanko is the member of IEEE, which is the Institute of Electrical and Electronics Engineers. He's currently working towards a PhD degree at the Department of Electrical Engineering and Computer Science at Howard University in Washington, D.C., USA. His research interests include machine learning for structured data, securing network devices, and coordination of multiple flying autonomous systems. So his um, so his talk today would be about an interesting topic: the application of machine learning in cyber security. And his work is titled "An Unsupervised Graph Neural Network Approach to Deceive UAV Network Reconnaissance Attack." So, without further ado, I will give you the floor, Adrien, and uh, you can start.
Okay. Thank you, Jonas. Thank you for the kind word. And really, I want to excuse for the delay. The first thing that I observed is like the town where I am right now. There was a storm, so this has disconnected the Wi-Fi from home. So I had to move to the public library to get connected. And sorry for the delay again. Okay, my topic is today is about using unsupervised neural network to deceive UAV network reconnaissance attack. This work has been already accepted to Infocom, so now the problem is just waiting for the release to the public. And let's go. Okay, I work this under the supervision of Dr. Charles Kamwa and Danda Rawat. Dr. Charles Kamwa is with the DoD, Department of Defense, and my supervisor, Professor Rawat, he's at Howard University.
Right.
So we go to the motivation, problem, approach, and result. So I won't spend time here. The point is just the mobile network is subject, the mobile UAV network is subject to cyber attack. Here, when I say mobile UAV network, it's just about simple wire the drones when they all connect together. They make a network, and because they share information similar to computers, therefore we can attack them. And because now there is a movement who are using this kind of network, meaning that there will be more user on this kind of network. And therefore, meaning more user means also we can have the good and the bad user. And therefore, once the UAV have found the optimal point, is they become like a a computer network, because the UAV can be mobile to find the best point to be in space before sharing the connection. But once they do that, they kind of become a static network. But after doing that, everyone who connects to the network can now apply all the elements that goes into computer networking, and therefore attacks, cyber attacks. And for network reconnaissance attack is part of the cyber key chain, meaning that it's just a reconnaissance process to know more about the environment. And here the environment is here about the IP addresses, which one connected to which one, and also like what is protected. Because if you see a firewall, you can guess maybe something is protected there. So that's the part of reconnaissance, just to know more about the network, and knowing that allow the person or the attacker to move in and to go out easily. And one issue with this one is like it's hard to control it, because you can prevent people to just move around the network, because it means like you are blocking also the user that just do its normal behavior. And that's one difficulty with this kind of reconnaissance attack, because if you really want to stop it, you will have to stop the traffic, which is not what is needed right now. So here is just an image of what looks in network reconnaissance attack. In the case we take with the UAV node, is like the attacker has no knowledge about the network, and he sent just a request. And the UAV, because trusting the request coming from a normal user, will respond with the defender network, or like with the correct configuration. And at the end, the attacker gets the right configuration, and now he can do whatever he wants, or like move or plan better the attack. So the system, how we design it is designed to respond to requests. It's simply like if I ask you a question, you answer. That's the idea. So now the point is, if we cannot prevent you the answer, can we decide what should be responded? And as I say, we don't want to stop the request, but at the same time, we don't want to leak the correct network configuration. And the answer is yes, we can decide what we respond. And that's where it goes to how now we deceive the attacker by giving false information or incorrect information. And here, what are those information that we are giving out? Those information are network configuration, or it will be fake network configuration. And therefore, at the end of our defense strategy, that's what we expect to have. The attacker has no knowledge before, and after he send the request, the UAV know we pull information from a fake network, or where there is safe false network configuration, and provide those information to the attacker. So at the end, the attacker will have network configuration, but not the one that correspond to the true network we are defending. And how to obtain this fake network configuration? The one idea is to creating or using what exists. The creation is hard because it really goes to making everything right, and that's consuming, because the network we are defending is a network that once we already created. That means it's a network we also created, and we know how hard it is to create that network. So that's why we prefer to defend it than having to create such network every time an attack occur or a breach occur. So one way to not have to create every time something that's so difficult is to use what already existed. And that's where we are going to look about all network or test network or network from others, that we know, okay, if the information there is leaked, it doesn't matter. So now the point is, okay, how do I know this network is good to use instead of my network? And that's where comes graph neural network, because this kind of deep learning model is used to really learn about structured data. and it takes information from graph theory, from deep learning, everything combined is just to learn about the structure and also about information. And so when we look at the UAV network, we can see that it can be well modeled as a graph data, meaning that it's structure plus information on top of it. On the left side, we have a UAV communication network. On the right side, we have a graph data. We can see that how they connect by the edge, the line between every node of UAVs. And when we say graph data, because on each node of each line, we have information that is added. And that's where we convert it. That's how we see that the UAV network can be converted to a graph data. And here is an example of a different graph neural network approach to aggregate the information. Here is like how a graph neural network works. It's just like you are connected with we have your friends, okay, people with trust and less trust, but you get information from everyone. So now from your network, I will say not from everyone, because you can be first, second, third friend of someone. I know this through this person, through this person. So now you are getting all the information from them, and now you add your own information and you try to predict your next move based on that. So that's why we see on the left side, like the network here is just taking information from some of its network, of its friend, of like neighbor, not all of them at once, but some. Aggregate this information and therefore try to predict the next state. So you can see the red node is really the one that's doing that. The other node are just feeding information. So, and it's that for every node in the network. So each node is aggregating information from its neighbor to compute its new state, the next state. That's what's about the graph neural network. And now different approach exists to do that. But the difference why we choose our model, which is the deep graph informers, is because how the problem is set up for us. When we want to compare two different network, here we don't know which one is correct or which one is wrong. There is no information about this one is close to this one. There is no kind of information. There is no ground truth. So therefore, we are receiving two network and we are asking, are they close or are they not close? This fall because there is no ground truth. It falls in the domain of unsupervised learning, and deep graph informer has been built with that approach of using unsupervised learning, meaning when there is no ground truth information, how we can compare the two network. And here is the model itself, like the architecture of the model. The idea is just we give the two network, we simplify just by giving just a node and its neighbor. Now we encode those information, and after encoding those information, we get a new state for each node, and we now start to looking how to discriminate between those two. And here the other difference is like we take the defender network and we find it summary level, meaning that we take the whole graph and we associate to it a single vector that we say, okay, this is the representation of this whole graph, its structure and the information on it. And now we take that one, single vector that represents a graph, and we compare it with the node representation. By doing that, we want to say, okay, this node belongs to this graph, or this node does not belong to this graph. That's what we are looking for when we look at D. D allows us to tell us, oh, this node is part of this graph, or this node is not part of this graph. By doing so now, the model knows, okay, this node is part of this graph, and therefore can differentiate the network, because it will say, okay, I can say this network is not this network. Or I can say at the same time, this network is close to this network, because I can tell, okay, these nodes are close to this kind of graph or this representation of the network. That's how now the model is able to find the similarity between two graphs and tell, okay, these two graphs are close or these two graphs are not close. In the sense that the two graphs are close if maybe the node between the graph 1 appear to be part of the graph 2. Therefore, we can say, oh, these two graphs are similar because I can see that the node of one graph is too close to the node of another graph. That's the approach behind deep graph informatics. And the difference here, we use two encoders compared to the original model to make the insight of the difference, because why two encoder? We want to be able to use any kind of graph, meaning that a graph can have 1000 nodes and another graph can have 100 nodes, and we want to compare those two graphs. And if we found that difficult to use the same encoder for the two, because the number of nodes, how to process the number of nodes at once, make it harder. Like the adjacency matrix, the size is too different when the number of nodes change. And so we prefer to use two encoders so that it can deal with every kind of network size, and it will become easy once we get the representation now to compare them. So the two encoders are useful when we put the two graphs as input, because the two graphs are too different. But once we go with the representation, now they are in the same space feature, and therefore we can compare them easily. So now once we do, our model just is going to give us an ability to compare the network. But now, how to distinguish the network and say these are close and these are not. That's why we define two parameters: a ratio between the network representation, the ratio of the norm. We compare the ratio of the norm and also the angle between the two vectors. And like that's why we use the cosine. And that's how we plot this on a graph, on a 2D plan, to see now, okay, if two graphs are close, that means they share a lot of similarity together. If they are not close, that means they do not share it, and therefore we need to not use one with the others. So here are our sample data. These our different graphs that we tested. The red one are viewed as ground-based station. The blue node are UAV forwarding node. The light blue are UAV switches, and the green one are end-user laptop, phone, and so on. And the information that we consider are IPs, mask, port, device types, and feature of each node. And so once we do the mapping, we do all the computation, now we see that each graph has been plotted, and with the information on it, the norm ratio, the angle, everything is there. And now you can see, okay, our dependent network G2, he has angle 0 degree and norm 1, because when you do the ratio of the same value, you get 1. When you look at the angle between the same vector, you get 0. So that's when the dependent network is always in position of 1, 0. But now you can see the other network, how it is at the place on the plan. So we can see, okay, G4 is close to G2. So meaning G4 is the network that I can use to replace the network G2. Meaning if I want to deceive and to defend my network G2, it's better to use G4 than any other network. And we try to understand why it predicts that way, and we can see, okay, for example, the structure of G2. When we look at the structure of the red node, the blue node, they are forming a line. We see that between G2 and G4, the red node and blue node are all on the same line, compared to, for example, G1, where the red node and blue node form a star topology. That's kind of different of topology right now that we can see. We can see G5 remains looks closer because we can also see a line topology with the red and the blue node, which correspond to like what we have in G2 and in G4. But on the other point, that you see how it already see that the topology impacts the closeness between the network. Now the size, you can see also the size like a G3, its size is really it's like going, it's looking far G3 or G1. And if you compare to G2, their size are small compared to G2. And we see that the more the difference in topology impacts more on the ratio, because G1 has a different topology than G2, but G2, which has a close topology in sense of line, but it's not in terms of norm too far from G2, but in terms of angle, it's really too far. And now that's where we can see about the feature that impacts now. Maybe, for example, on G3, there is no switches, and you see the angle is really the widest, no switches, compared to other model where there is switches at least, and the angle is not there. So that's kind of different that we try to explain and say, okay, that's how the model view it. The topology and also the existence of some particular feature like switches impact more the angle, and topology impacts more the ratio. And that's how we can see, okay, G4 is the closest because it has everything with G2. While G1, which has something, is defined in terms of size, which has a topology completely different compared to the remaining to G2. And G3, which has a small size and therefore has the widest angle compared to G2. So that's how we see, okay, G1 for most is good, and therefore our approach, how we can choose a better network to defend our own. So that's everything was about this work. And if you have any question and more, I'm ready to take them. Thank you for your attention.
Thank you, Adrien. Thank you for the talk. Uh, it is the moment where I will turn online and see if people have questions. No, if I don't see questions meanwhile, but hello online. Uh, can react in the chat and ask questions. Meanwhile, I would just like to ask. Maybe I will go with the first question. So I wanted you to come back a bit on the threat model here. From what I understood, you have
Okay.
a network of a UAV's network, and
Yes.
an attacker wants to know the network configuration from a given
Yes.
UAV, and then you want
Yes.
to return a fake configuration to the attacker. So
Yes.
is that so? Can you a bit because I've seen graphs and I'm wondering what to the G1 G3s are, which one is the correct configuration and which one is supposed to be the attackers or the defenders returning.
Okay, the defender network is G2 here.
Mhm.
The first one, do you see?
Yeah, we can see that.
Yes, is the defender network. Now, what the attacker will see here, it is you now, the defender has to choose between what he wants from this pool of network G4, G5, G1, G3. And the defender doesn't know at first what network is the best to choose to deceive the attacker. So now what he used now this approach of using the deep graph informal data tried, and now at the end he get this map that tells him, okay, you should use G4. It is the closest network to yours, meaning the configuration that he will have to use will be the configuration of G4.
Okay.
Those configuration will be enough close to his so that the attacker will not know that it is not inside the G2 network, but whether inside the G4 network.
Mhm. Okay. So, and on that, maybe a follow-up question to that. So you presented a discriminator at some point, but
Yes.
how do you generate the fake? Where does the fake network configurations come from? Though, like, is there a generative part also, or
No, that's what I said is here in this work, as I discussed earlier, you can generate or you can use existing network. So I do not generate.
okay,
I use existing network, meaning I have a pool of networks,
all right,
computer network. I have a pool of them.
all right, all right, all right.
So and I just compare them.
Oh, all right. Then you generate that. Then you take the one that misleads most the
Yes,
attacker. Okay,
yes.
okay, okay. Oh, okay, all right. While waiting, yeah, while waiting for questions online, maybe here you can, yeah, wanted to ask about page 14, yeah, right where you are, about like, can you explain a bit more about the components of this UAV network, the different colors, and what are their roles in
Okay, the red one is like the ground-based station, meaning that the antenna that we can see when we walk around and the communication antenna. And the blue one node are UAV node, meaning that drones that can receive information from the antenna and passes to another drone. The light blue are what we call UAV switchy, but they are also drones too. But the difference is that they will all directly communicate with the end users, meaning laptop, phone, directly. That's those like those labels. It's kind of similar to what we have in computer networking, but here it's just for drones because it's just sharing information, transporting information from one point to another point, and therefore some drone will do this kind of work.
okay. Um, so and that I'm wondering what is can you give us a like a scenario where you have this kind of network, like where you have maybe some UAVs and some and people or end users. Like what is a typical setup for that? Typical application.
Typical application will be just, for example, if there are a lot of events or disaster, those are maybe the most hurt. In case of events like if you have a lot of communication from stadium, even uh, how do we say buildings, and you want to share that information, it just like the UAV would be here to compensate if you cannot share that information. That was it. Event stadium, that's for when you're in town or even sometimes disaster or region where you don't have you cannot install a lot of base station antenna, and a region where it is too spread or people are spread around. So that's where you can use the drone to transport, because installing a base station is costly compared to a UAV, which is mobile, so you can come, share the information, and maybe move back for the time that you need it. Instead of having to install a base station in area where the population is not maybe too much, but where they need the communication. So the UAV are really good also for doing that. for share for people when people are spread. And that was it. You can have events, temporary events where you can be a lot of traffic. If I will take the geo, if I will take the, because the geo are in down, so we may not see directly the impact because it is really close in the area, but you can apply in a town, completely in a town, or connect different town. And where you don't need to install a base station, meaning a big antenna,
Mhm.
and therefore you can use drone to cover those area. And after that, you can move, you can remove the drone and also go to do something else. So I would say rescue, if it's not rescue, lit area where the people are spread, wide area where people are spread, because the drone has the ability to go higher and to get above towers, above towers. So now, even when there are towers, to in town, when there are a lot of towers and the antenna, you don't want to install antenna on top of towers or on top of houses, you can have the drone doing that, meaning reducing the impact of antenna affected health issue. You can have drone which can go above the tower, still communicate with the people directly. So in town, let me show this kind of network as you can see on the left side. So you see the antenna are down and the drone are upstairs to perform the transfer information from one town to another town. If not, you will have to, instead of connecting, of putting more antenna on the ground, and that is really costly compared to having drones doing it, which can be mobile and move to different location at time it's needed.
I see. I see. I see. Uh, I have a follow-up question, but I think I will take the first question online. It's from
Okay.
Arsene. Let me show you. Arsene asked, "What would be the financial benefit of this?" I don't know if you have something to say about that.
Yes, for the financial benefits is cost reduction. Producing drones is cheaper. There is no way compared to I can produce. You can produce, but I can't say me. But if you look at the base station, a ground antenna, where you look how it goes taller, how you need to put the antenna on top, also the health issue because people that why the antenna are really hard to be on top to not really mingle with the population, and also because of the site, because when it is up it really have no obstacle, so that installation is costly. And that's why if you look go back in our country, they do not install a lot of base antenna. For example, Cameroon, it is costly. But compare now with drones, which is cheaper to have, cheaper to produce. You can have 100 of them. First, so them more, and you can just put them wherever you want, in the sense that they are mobile. So you deploy them, they go, they can stay for a period of time. Okay, so they cannot stay forever like a base antenna, but at least they can stay then a number of hours depending of the battery that you put on it and the information is changed. And therefore you can deploy them. And once you are deployed them, come remove them, come back and move to another city if you have done whatever you want here. So in terms of financial benefits, it is reduction of cost. It reduce the cost. That's why they invest in drone communication right now because it's easy to produce drone. They can be destroyed easily. They can be replaced easily compared to a base station. They can go higher and also less risky. So you don't need to send a person upstairs for inspection because drones are really good also at inspection. and they're even used on ground-based station now for inspection. So now, if you can, instead of standing a person, you use the drone. Inspecting the drone is easy too, because you just have to put it down at your level and inspect the drone at your own time and effort easily. So the setting up is easy with the drone. So it really gives advantage of cost.
Okay. Okay. It's uh, so there is cost reduction, but I would you said uh, they are less risky, but I'm wondering about how about the network reliability though, because
Yes, that's why they invest research are ongoing to have reliability now because of Wi-Fi. That's the part of having many of them to ensure that they are reliable, because we know they cannot send it. Their range is shorter than ground-based station, but you can have many of them, and so that's why you can send or share information.
all right. One
But
question. Go ahead.
yes, yes, please.
Yeah, still about the setup and your architecture. So just to understand the base stations that are here. So it's the reduced cost, but you still have some base stations. Are those base stations also mobile?
No, no, the base station are not mobile, they're on the ground. The base station are on the ground.
No, not mobile by okay. Maybe I'm using. I mean, when you took the scenario where you have an event and you don't want to invest in base stations or like traditional ones, and you said you could move easily. Like, are these base stations that you
No,
have?
no, 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 no. When you say move easily, I'm talking about the drones.
Okay, okay,
You
okay,
can get back all the drone in like what to say, in your car, in your truck. They all come back in your truck, and you move with your car with all the drone. Once you deploy them, you do whatever you want to do. You put them back, and you go. And
okay,
also bring another issue, but it's not part of this work. It's like even the attacker now can have its own drones, mingling with your own drones,
okay,
because it becomes it allows you to have like an extension of your personal router if you take it personally, meaning the drone can go where you want it to go. You stay at your place, and the drone can go where you want it to go. So now you extend the drone. Is that why they want also autonomous drone, so that it can go farther and do the job? Okay. So yes, you can make them come back and move to another place. That's not the ground-based station, but only the drones.
all right. Uh, don't see questions online. Another question? No, I don't see. Maybe I can ask one more. Don't know how much time you have with us again.
Because okay, I have time. I know I planned for like 2 hours.
Okay.
So,
Okay. I don't see questions online, but I can ask you some of the questions I noted down. So, you said you were using a pool of data set of network configuration. So, in general, where is your data source? What is your data source? Where do you have take your data? Is it public data or proprietary data?
no, for this work, I had to create my own data, and that has been something that I discovered through this work, that computer network is not so easily available. It is in fact not shared at all. Meaning, this is one of the kind of data that is too secure. Company, public or private, do not share their network. They simply do not. Obviously, you can think that, oh, there is a lot of calls on computer networking. So obviously that means data should be there. No, Absolutely not. Yes, there are courses to learn to how to create, to teach you the basic, but you will not find a computer network configuration out there. It what you will find, okay, they has been already corrected, but in this case they were not too much useful for me. Or if not, even I will have to how to say to build them again to scratch them. It doesn't say that it doesn't exist networking, but it means that for the one that I needed, it was difficult to have them. It was difficult, so I had to create them. I really had to go back on my notion of networking that I learned at AIMS, African Institute for Mathematical Science. And here I had to create the small network, trying to respect everything goes into the computer networking configuration. But it's not easy. I don't know if you can find a computer networking like telling you, okay, this IP address, this. You can have some, but either they are old or either they're already focused on particular domain like security in the sense of detection. But here I don't do detection, so what I needed was really just the plain network configuration. That was what I was needing. And if not, okay, I will also need the traffic, but I didn't use the traffic in my networking, and then I just use the plain network configuration. You see, when you look into traffic now, if you look at the packets, how many have been sent, the times for sending, that's now where the queuing approach that has been used, that's part of the traffic. But well, we'll focus more on just the simple plain configuration IP address, how they connect the switches, how they have been segmented. That's only what I was focusing on.
All right. And how confident are you on how do you generate how do you make sure that you generate diverse configurations or that it reflects what you would get in uh, configurations that you have in a real life situation.
I can, okay, it is small, so I can say I'll put all the information there. So there's some information that I left out because, as I say, creating a network is tedious. Creating a complete network, computer network, or UAV network, it is tedious to have everything working. So even those part of IT dependent, they admitted it's not easy because I even discussed with some. So I left some parts out. I left some parts out. For example, you can see the queuing theory, as I say, the network. I left this part out. I remain with the simple one that like you need the IP, you need to connect the gateway, the IP, the net, the mask. I focus more on that one, which are the basic to have a networking working. So that's the part that I use. Now the remaining how well the segmentation and the switching backend, that's because you see when you learn networking is more about, okay, for example, we use packet tracing. So on that one, what you were learning was just your IP addressing, your gateway, your mask, and once you test with that one, it works, it works. You don't need more to how to send the packet, and once work is enough. And that's the notion that I use for this work.
That's cool. Um, uh, Maybe I'll go with the. Let's talk a bit about the representation. So, can you tell us about like uh, the graph representation of your network, and also when you use the graph neural networks, uh, is it um, is there particular representations that you could use and uh, or the extractors or that you can the encoders that you mentioned, the
Okay,
different types of encoders that you use, and then how do they compare if that's
okay, for the encoder, first of all, I gave to okay the data structure. You just like my data was such as a dictionary, and once the mapping was simple, is like to transform the node with its information into a vector. That's the simplest approach that I use. Like you gave me a node with like the IP, the mask, any information now, I just try to convert that into a vector. And once I perform that vector configuration, that vector transformation now, I will use it at that level down, I will apply the encoders to to really now start learning the feature of the network of the node, because it's like okay, if you give me IP address, I find just a way to take the IP address and make it as a vector. That's really, I would say, how it works in general for any machine learning model. So you just convert that number into a vectors, and after getting that vectors, even if you tell me that device type, for example, the device type, I use the one hot encoding. If it is a router, it is a 100. If it is a switch, it is 0100. That's kind of encoding, one hot encoding that I use. Um, that's everything that I use to now have the vectors and move forward with the computation. So the encoder here, and the particular encoder was the that I used was the graph convolution network to in my encoding. So yes, after I have those vector, I use now the graph convolution network to do it.
okay? I have a question, follow-up question from Naomi. Uh, uh, Naomi says, what information is used to construct the edges? That is the link between the nodes, please.
For this case, I transfer any age information to the node. So meaning my age, I do not have information on age. Simply age and simply connector. And when I say I transfer everything to the nodes, like okay, I know we can see that an age we say connecting to node, meaning I can take the IP address, I can take the gateway, and say okay, my age will be made of these two kind of IP address also or no. In this case, I just say okay, every node will get all the information, and I will just connect this ID node with this ID node that will make my age. So that means the age has no information in this world. All the information are stored by the node. Meaning, okay, all the IP address, the mask, anything are stored are information of the node only. So the age will just be connecting this node, node 1 to maybe node 10 or node 1 to node 2. That's all. Meaning going to this just age has been like if I go in the agency matrix will be just 1 or 0, connected or not connected. So I did not, I know I could have done that, but I prefer to focus on giving the node the information.
In that case, don't know if Naomi is fine with the answer. So, but how do you, in that case, if how do you represent the graphs information, like the networks, like the network configuration information, if you just take the nodes, like what is
No,
into
no,
the
for example, when I connect, when for example in the networking, when you take, you say two computer communicate, what happens is like the at one node, you at one computer, you give it gateway,
Mhm.
and the gateway is usually another device gateway. So in that case, they have the same, like the gateway of this node correspond to the entry of the other node. and therefore those two are connected. So I ensure that within my node, so this node as the gateway information, the other node are the same gateway information. But for the edges, I will just say, okay, this node, maybe ID1, is connected to node ID2. So for the age, I will just say 1, 2 age. And so for the age, I will not add information. I will just say 1, 2, meaning the age going from node 1 to node 2. That will be the connection. But at the node level, the node 1 will have a gateway, or maybe, I don't know, dot point 1, and the other node, node 2, will have another entry that will be dot 1 for the same remaining network information. So you see, they will have the same information if they are connected in terms of this gateway for this node correspond to this, like the one we have in networking exactly. You have to specify the routing table in a computer network. So, and that's how I see that, okay, every node we have knowing where it's going to send the information. But the edge will not have information, so I store the information only at the node. You have your IP address, you have your gateway. You have the IP address, you know when you need to send that information. That's the same process that I use. In similar way that we do in computer networking, that you go on the device and you do the configuration. You add the IP, you add the mask, you add the gateway. You go on another device, you do the same configuration. You add the IP, you add the mask, you add the gateway. And therefore, I view that, okay, that means each node gets its own information, like, or each device gets its own information. And for the now, the network for connecting, I will just say this node is connected to this node, because when you do the graph structure, you have to precise the age. So
Okay.
hopefully it's okay.
Yeah, I don't know if you can see the chat. Naomi had follow-up questions and comment. She said, first she said, so what's the meaning of two nodes being connected? The interpretation in layman's term. And she says, okay, I understand that no information is embedded in the edge. So that's the edges are not weighted. Maybe
Yes,
that one.
the ages are not weighted.
Okay.
So the connection is just as the simple unweighted graph,
Okay.
meaning just you just say that they are connected by in your graph, but no information on the edge.
Yeah, and she says, so the gateway is the means by which the nodes were connected, if I understand correctly.
Yes, and I go back again. Yes, that's how we do in computer networking.
Okay.
You when you use maybe packet switcher, you want to connect to device, you go on each device and configure them. And when you configure them, you make sure that the gateway correspond to the same is the same. So that's how I play this one.
Okay. Thank you. Um, more. I don't know if people have more questions. Um, um, so, in this work, you maybe it goes beyond you presented here. The threat model you presented is like I mean, the threat you presented is Reconnaissance attack. So,
Yes.
is there another threat? Are there other threat models in this situation that you could still use uh, your
Approach.
your approach, or yeah, can you tell a bit more about other threat models, or is it um, um, What?
Okay, so I focus more on one part of the attack, which is just getting to know the network. But the other part, once you know the network, you plan, you deliver, and you once you deliver, you have you it gets executed, and so you take control, and that's where you are successful. That's part of the element of the cyber kill chain. Okay, but if I look at that way from with our approach we focus mostly on comparing network, on comparing graphs. So if you have to decide where you need to compare, yes, our approach is useful. Where you want to compare to be able to represent, and also you don't have anything ground truth, because here it's like you just give you two network and we tell you is it there, are they close or not. You don't know which element particularly we are looking for, but we just want to know are they close enough. So that's why it is unsupervised. Like you don't know, you have to train a lot to okay it's now to distinguish your own feature, to decide okay these two are close because of that and that. So now all the test model, for example, if you look at all those element of cyber teaching that I just enumerate, mostly there is a detection. And in detection now, different element plays there. Because in detection, while you try to get the signal, a weak signal usually, to that will let us know, oh, this move is not good. But since a computer network can be represented as a network or the graph data, now if you want to compare between two graph and know, okay, in one graph before two state, there were no signal and there were signal. Now you can see that our approach can play a role there. Can play a role there because if you take two state of a computer and between the two state there may be a move from the attacker that is so weak, or it's so discrete that you cannot see. Now you can compare those two states, and because those two states represent the network at two time step, now you can compare the two network using this approach too. And now you will have to, but the point is that you have to ensure to have enough data to make the difference between two time steps, so that the model will be able to identify those move from the attacker or those weak signal, so that when he will look those two graph and will say, oh, something is not going, something is wrong there. So but
Right.
in that sense you will more maybe focusing on not closeness but more on like difference, because though it will be always the same network, which means obviously it will be close to its to himself to itself, but you will be able to focus more likely on how far they are, to be able to know okay here are the signal that create that distance between them. So you will have this one maybe one link going, and so you will have to look okay to make sure that link is really create a lot of difference, so that the network, so that the model can call this movement easily given to network that are already close. That's another way this kind of approach can be used.
Okay. Uh, Now we have questions about the architecture. And so she says your DDI model has two layers according to the image on the slides shown. Uh,
Two layer, no, 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 no. That's just the step of processing. It's not really two layer.
okay.
But we can see, okay, we can see when you see two layer, is that it's not the same layer that's repeated. It's the different step of layer, the different type of layer that goes in. But it's not the same layer. So if you want to talk about the layer, it will be repeating all what we see on scan twice. So it's not really about the same, it's just the layer, the complete layer has different step of processing. So you give first the X and AX, just the input. Now we encode, we get the HX, and after we get those encoding, now we discriminate with D, and now you get the output and plus and minus. So this is just the different step of the processing. The all that's going just in one pass. Now I can use more layer, maybe the encoder I can use 2, 3 layers of encoding, or maybe I can just on the discriminator use more. So if I want to add more layer, it will be more on the encoding of repeating the encoding many times before, but in our work I just use one layer encoding to reach my result.
Okay, so if you understand well, so you have your two graphs. You want to compare
Yes,
x and y, then you get the
yes,
two
exactly.
representation epsilon one and epsilon two in different the both branches, and then that's where your discriminator ends enters begin.
Yes,
Yeah.
yes. The X term is the dependent network, the Y is a potential fake network. Now we encode both of them with epsilon 1 encode the defender, epsilon 2 encode the potential fake network. That's why we get the HY, the HX. Now the S that we see with the wingering arrow,
Mhm.
now it is summary level of the defender network. It summarizes the graph, the defender network at once. It summarizes, it gives a single vector for the whole graph. And now what the D does is like it takes each node of each graph and compare that node to the summary vector of the defender network. The discriminator has to tell us if a node is part of the defender network or not. So D tell us that is this node part of the defender network or not. And
Okay.
that way say plus or minus.
Okay.
It has to say a lot plus for the node from the dependent network, and it has to say a lot of minus for the potential fake network. So now if you cannot say that, or it say a bit less, now you can see that the potential fake node is really close to the dependent network. So meaning that okay, this potential fake network is the best candidate to match the dependent network. And that's how the discriminator have to, and that's how at the end the model can tell us which network are close to the defended network or not.
Okay. I think you've cleared Naomi's questions. He says thank you for the explanation. Um, yeah. Are there any more questions? Meanwhile, if you have some comments to make, you can feel free to make.
No, the comments like thank you for the question. Really, yeah, Jordan, great question. I mean, great. I will see with great questions. Yeah, it's really a pleasure to answer them.
So, um, I don't know if looking online, maybe just let's see if someone pops a question. Otherwise, we'll call off this session for today. Um, any more question online? Okay. Um,
Just
then
my comment will be like we are not going to see the others. It will be only you and me, right?
yeah, you can just because the live chat, then you could check the chat. They can react on the chat on YouTube chat, but we are the only two connected.
I I don't have. I'm not on the YouTube app right now.
Oh, okay. So yeah, normally, so the last comment was from Naomi, saying, "Thank you for the explanation." Um,
So you say I can see that. Okay, let me just
I don't know if
let's see. I'm
uh,
not on YouTube, so I will try.
uh, um, So for those who are maybe joining this live session now, you'll have the recording later on the KmerAI website, on YouTube channel. Sorry, so you have it. You have the recording as well as the past KmerAI talks. Um, Adrien, you are checking the YouTube, I guess.
Yes, yes,
Can
and
you
I'm
see it
really
now?
surprised. There is one person. Okay, yes, thank you, thank you.
Okay, okay, okay.
I will see, I'm checking now, I've seen.
Okay, okay. I think if there's no other question, I think we can stop it here. If you're fine with that, I'll stop the live. Uh, any last word or
Oh, thank you for having me. Really, thank you.
wish you the best for the rest of your HT, and thank you for coming today. And thank
Okay,
you everyone for coming. See you next time.
see you.